Welcome to part two of the groundwater lecture. Today's part of the lecture is brought to you by Grey Poupon. Pardon me, do you have any Grey Poupon? Actually, I do not have any Grey Poupon because, well, that condom was way the hell more popular in the 80s, and the stores around me do not have any in stock. So there's that. But the real reason that Grey Poupon has decided to sponsor this portion of today's lecture is that it is a Dijon mustard. Therefore, and as you'll see, the story of groundwater takes us to Dijon. All right, let's head to the Dijon Pas de Français. So this part of the lecture takes us to the lovely pond of Dijon, France. What you'll see in Dijon, France is some beautiful fountains or fountains that are constantly flowing, and something very important, boast very clean water. Holy cow, those stalactites on that bridge, that's super awesome. I've been like doing this lecture for 5 years, never seen those stalactites on the bridge, man. This is cool stuff. So, a fellow by the name of Henri Darcy, in relation to the guy from the Jane Austen novel, got curious about what it was that made these fountains so remarkable, and so decided to study them. So let's take a look at how these fountains worked and what Darcy was thinking about. So the way these fountains work is you have a river. Now, if you're in the time of France when these fountains were built, this river is actually pretty dirty. It doesn't look like this drawing, so I didn't have the time to draw the dirt, but I guarantee you this fountain is quite dirty. And so the way they sort of cleaned up the dirt is they had a bunch of pipes that led from the river down into the city where the fountains are, and there was sand in these pipes. And then the bottom of these pipes, you had a fountain. Here, let's see if we can get a. And so Henry Darcy wanted to understand what it was that made these fountains, how these fountains worked, and what principle they operated on. So he quickly was able to distill it down to a couple of parameters. So first, you notice that pipes that had a pipes that went further downhill tended to have more vigorously flowing fountains. So we're going to call this distance from the top of the pipe to the bottom pipe, we're going to call it the head drop. Now, a lot of people are like, wait a minute, head? What are you talking about, head? This is where you've got to use your head. What definition of hydraulic head is simply head. It's just a measure of potential energy. Water equal hydraulic head. It is a potential energy of water equal to the sum of the water elevation and the water pressure. And we're going to abbreviate this bugger with the term H. This is you'll see a number of abbreviations if you study this long enough, but the head drops. Let's the other thing that Henry Darcy realized was going to be important was the I'll just probably also just edit this here. This says DH or change in head. All right. Things that was going to matter was the long length of the height, or the distance. We're going to call this dl, or difference in length. That the longer the pipe, all other things equal, the less flow there was at the fountain. Now, third thing that turned out to matter quite a bit was the cross-sectional area of the pipe. So we get this to all things, or A, that is that the area cross-sectional area, larger pipes would intuitively transport more water. Yes, it's sort of feeling fairly elementary here. You just got to bear with me here. And then finally, a final product thing that mattered for this whole equation was the hydraulic conductivity, the ease through which water flowed through the pipe. You can also think of this as permeability. Well, if you study this more carefully, you realize these two are slightly different terms, but we're going to abbreviate this with a giant K. And that once you got all these things, you could then quantify flow rate, or Q. Q, which should be in volume per unit time. And so the way Darcy did that, and so the equation that Darcy came up with was the following. Q equals K times A times DH DL. And the cool thing is, we've been able to actually calculate this in some of the lab classes we happened. It's kind of a bummer that we can't hang out with one another because we don't have any lab activities, but we used to be able to do this and it was awesome. And someday we'll be able to do it again. Yeah. That about wraps up Darcy's Law. In the next portion of this lecture, we are now going to go into how do groundwater systems look like in nature?